Good morning, students. Today we'll discuss to find the residues of a given function at finite poles. So firstly, let us take a function f of z having a simple pole at z is equal to a. Suppose the function f of z that is of the form phi z divided by psi z. We are to find the residue of this function at the point z is equal to a. Now by definition, the residue of the function at the point z is equal to a, that is given by limit z approaches to a of z minus a into f of z. Putting the value of f of z here, this will become limit z approaches to a, z minus a into the value of f is phi z divided by the function psi z. Here these two functions phi and psi, these are analytic functions, so we can write their expansion by using Taylor's theorem. So the value of residue at the point z is equal to a, that becomes limit z approaches to a, z minus a into the expansion of function phi, that is given by phi of a plus z minus a into phi dash a plus z minus a whole square divided by 2 factorial into phi second derivative at a, and so on. In the denominator, we have the expansion of function psi, which is given by psi of a plus z minus a into psi dash a plus z minus a whole square divided by 2 factorial into psi second derivative a, and so on. Now, because the function f has a pole of order 1 at z is equal to a, so by definition of pole of order 1, psi of a, that will be 0. So we can substitute this value here. So the value of residue at z is equal to a becomes limit z approaches to a, z minus a into, in the numerator we have phi of a plus z minus a into phi dash a plus z minus a whole square divided by 2 factorial into phi second derivative at a, and so on. In the denominator, psi of a becomes 0. So we are left with z minus a into psi dash a plus z minus a whole square divided by 2 factorial into psi second derivative a, and so on. Now from the denominator, let us take z minus a common, and that will be cancelled with z minus a in the numerator. So by taking limit as z approaches to a, this term will become phi of a divided by psi dash a. So this gives us the value of residue of the function at the simple pole z is equal to a. Now, in the next theorem, we will derive the formula to find residue at a pole of order m. So let us take a function f having the pole of order m at z is equal to a. Then we prove that the residue of this function at the point z is equal to a is given by limit z approaches to a of 1 upon m minus 1 factorial into m minus 1th derivative of z minus a whole raised to the power m into f of z. Now to prove this formula, because the function f is having a pole of order m at z is equal to a, so by definition of pole of order m, the function f can be written as phi divided by z minus a whole raised to the power m. Here this phi is an analytic function which does not vanish at z is equal to a. Now the residue of the function at z is equal to a, that is b1, and by definition b1 is given by 1 upon 2 pi iota integral of the function f over the contour c. Now substituting the value of function f from here, the equation becomes b1 is equal to 1 upon 2 pi iota integral over c of the function phi z divided by z minus a whole raised to the power m. Now, this expression can further be written by multiplying and dividing by m minus 1 whole factorial, and here adding and subtracting 1 in the power of z minus a. Now, let us use Cauchy integral formula. According to this formula, the nth derivative of the function f at the point a is given by n factorial upon 2 pi iota into the integral of function f divided by z minus a whole raised to the power n plus 1. Now, if we use this formula for m minus 1th derivative, so we can replace n by m minus 1, and now we can use this formula here in the equation 1. So we get b1 is equal to 1 upon m minus 1 factorial into this whole term, that is the m minus 1th derivative of function phi at z is equal to a. So we have obtained the value of residue of the function at z is equal to a, which is given by 1 upon m minus 1 factorial into m minus 1th derivative of z minus a whole raised to the power m into f of z as z approaches to a. So we will use this formula in the numerical problems where we are to find the residue of the function at a pole of order m. Now, let us see some examples based on this. First example, find the residue of the function z cube upon z minus 1 into z minus 2 into z minus 3 at z is equal to infinity. Now, from the denominator, let us take z cube common. Z common from first term, z from second, z from third. So z cube is cancelled with z cube. So this function becomes 1 upon 1 minus z into 1 minus 2 by z into 1 minus 3 by z. Now we can expand this expression by using binomial theorem. This will become 1 plus 1 by z and so on. In the second, this will become 1 plus 2 by z plus here the higher order powers of z, 1 plus 3 by z plus so on. In the another terms, there will be higher powers of z. Now, from here, let us write the terms which are constant and the terms containing 1 by z. So that will be 1 plus 6 by z, and further we have the higher powers of 1 by z. Now, we already discussed that the residue at z is equal to infinity, that is given by the negative of the coefficient of 1 by z. So from here we can see that this coefficient is 6. So its negative will become minus 6. So the residue at z is equal to infinity is minus 6. In the next problem, we are to find the residues of the function z cube upon z minus 1 whole raised to the power 4 into z minus 2 into z minus 3 at the points z is equal to 1, 2, 3 and also at z is equal to infinity. Now, let us find the poles of this function. By putting denominator is equal to 0, we get z is equal to 1 is a pole of order 4, z is equal to 2 is simple pole, z is equal to 3 is simple pole. Now, first of all, let us find the values of residues at these poles. Now, by definition, the residue at a pole of order m is given by limit z approaches to a 1 upon m minus 1 factorial of into m minus 1th derivative of z minus a whole raised to the power m into f of z. Now, z is equal to 1. that is a pole of order 4. So m is 4. Substituting m is equal to 4 in this formula, this will become limit z approaches to 1, 1 upon 3 factorial, third derivative of z minus 1 whole raised to the power 4 into f of z. Putting the value of f of z from here, and we get limit z approaches to 1 of 1 by 6 into third order derivative of z cube upon z minus 2 into z minus 3. Let us change this expression into convenient form by dividing numerator by the denominator. This can be written in this form, and further we will reduce it into partial fractions by taking the partial fractions of this term, that can be written as a upon z minus 2 plus b upon z minus 3. After simplifying, you can obtain the values of constants a and b, and putting those values here, we get this expression in this form: z plus 5 minus 8 upon z minus 2 plus 27 upon z minus 3. Now you can differentiate this expression 3 times to get third order derivative, and then substituting the value in the formula for residue at z is equal to 1. This will become limit z approaches to 1 of 1 by 6 into, this is the third derivative of the given function. Now putting z is equal to 1 here, we get the value of residue at z is equal to 1, which is given by 101 divided by 16. Now z is equal to 2, that is a simple pole. So the value of residue at z is equal to 2, that is given by limit z approaches to 2 of the function z minus 2 into f of z. Putting the value of this function f here, z minus 2 is cancelled out, and in the remaining part, let us put z is equal to 2. So we get the value of residue at z is equal to 2. This is given by minus 8. Now the value of residue at z is equal to 3. Z is equal to 3 is also a simple pole. So the value of residue at z is equal to 3 is given by limit z approaches to 3 of the function z minus 3 into f of z. Putting the value of f of z here, z minus 3 will be cancelled out. In the remaining part, putting z is equal to 3, we get the value of residue, which is 27 upon 16. So we have obtained the values of residues at finite poles. Now residue at z is equal to infinity. Yesterday we discussed the theorem, the residue at z is equal to infinity, that is given by negative of the sum of the residues at finite poles. Now all the other poles are at z is equal to 1, z is equal to 2 and z is equal to 3. Values of residues at those points are 101 by 16, minus 8 and 27 by 16. So the residue at z is equal to infinity is given by negative of sum of these residues, that will become 0. So in this way we have obtained the values of the residues of a given function at all the poles. Now in the next problem, we are to find the residue of the function cosecant z. First of all, let us find the singularity of this function. Cosecant z can be written as 1 upon sin z. Its singularities are given by putting sin z is equal to 0. So we can say that z is equal to 0 is a simple pole for this function. Now this is simple pole. So by definition of residue at simple pole, this is given by limit z approaches to a of z minus a into f of z. Here a is 0. So this will become limit z approaches to 0 of z by sin z, and this limit is 1. So we have obtained the value of residue for the function cosecant z. In the next problem, we are to find the residues of the function z plus 3 divided by z square minus 2z. Now, the singularities of this function are given by putting z square minus 2z is equal to 0. So, the poles of this function are given by z is equal to 0 and z is equal to 2. Now, these are simple poles. So, by definition of residue at simple pole, residue at z is equal to 0, that is given by limit z approaches to 0 of z minus 0 into the function. Z is cancelled out with z. In the remaining part, putting z is equal to 0, we get the value of residue at z is equal to 0. This is minus 3 by 2. Now, residue at z is equal to 2. By definition, this will become limit z approaches to 2 of the function z minus 2 into the function z plus 3 divided by z into z minus 2. Z minus 2 is cancelled out. In the remaining part, putting z is equal to 2, we get the value of residue, which is 5 upon 2. Now, let us discuss one more problem based on residues. Find the residues of the function z plus 1 divided by z square into z minus 3. Now, the poles of this function are given by putting z square into z minus 3 is equal to 0. We can see that z is equal to 0 is a pole of order 2 and z is equal to 3, that is a simple pole. Now, by using the formula for residue at pole of order m, here m is 2, so this will become residue at z is equal to 0 is given by limit z approaches to 0, 1 upon 1 factorial into the first order derivative of z square into f of z. F of z is z plus 1 divided by z square into z minus 3. Z square is cancelled out and we are left with limit z approaches to 0 of the derivative of function z plus 1 upon z minus 3. Now, using the division rule of differentiation, finding out the derivative and putting z is equal to 0, we get the value of residue, which is minus 4 by 9. Now, z is equal to 3 is simple pole. So, the residue at z is equal to 3, that is given by limit z approaches to 3 of z minus 3 into f of z. Putting the value of f of z, z minus 3 is cancelled out and putting z is equal to 3 here, we get the value of residue, which is 4 upon 9. So, these were some of the examples of residues of a function. You can do more examples from the book based on residues.